Good day, everyone. I am here to present our research titled A User Interactive Vision Based 6 Degrees of Freedom Robotic Arm for Real Time Object Detection and Grasping. This work has been carried out in the Department of Biomedical Engineering at Rajalakshmi Engineering College and is presented as a part of the ICDTDE 2025 Spring Conference. Our research focuses on developing an intelligent and affordable assistive robotic system aimed at supporting stroke patients in performing daily object manipulation tasks. Stroke remains one of the leading causes of long term disability, and one of the major consequences faced by stroke survivors is impaired motor control. This impairment affects their ability to perform even basic object handling tasks such as reaching, picking, and placing items. As a result, they become increasingly dependent on caregivers, which affects their independence and quality of life. While there are existing rehabilitation systems and robotic manipulators are designed to support stroke patients, many of these solutions have important limitations. First, most advanced assistive robotic systems are extremely expensive, making them inaccessible for many users and unsuitable for widespread adoption in rehabilitation centers. Second, traditional robotic arms rely on predefined movements and lack real time vision capabilities, which means they struggle to adapt dynamically to changes in the workspace. Third, many systems do not offer user friendly interaction methods. They still require significant manual control or programming knowledge, making them unsuitable for elderly or physically challenged users. Addressing these gaps, our objective was to develop a system that is intelligent, adaptive, low cost, and easy to use, one that can detect objects visually, understand the environment, and respond to simple user voice commands. Our proposed 6 degrees of freedom vision based robotic arm addresses all these limitations by integrating deep learning based perception, inverse kinematics principle, microcontroller based control, and natural voice interaction. The main aim of our research is to design and develop a low cost, vision based 6 degrees of freedom robotic arm that can assist stroke patients by detecting, tracking, and grasping objects autonomously. To achieve this aim, we defined our four primary objectives. First is to integrate the real time object detection using the YOLO V8 deep learning model. YOLO V8 offers fast and accurate object detection, which is crucial for dynamic and unpredictable movements. Second is to extract precise object coordinates using OpenCV so that the robotic arm can understand where objects are located within the workspace. Third, to compute the required servo angles for each revolute joints using inverse kinematics principle. This allows the arm to position its end effector accurately onto the targeted object. Finally, the aim is to control the entire robotic arm using an ESP32 microcontroller and integrate a voice based interaction module. This allows the user to operate the system hands free simply by issuing commands such as pick or place actions. By fulfilling these objectives, we aimed to create an affordable, intelligent, and interactive robotic platform suitable for assistive and rehabilitation applications. Coming on to the methodology section, the mechanical design of the robotic arm plays a crucial role in its overall functionality. We designed the arm in Autodesk Fusion 360, focusing on joint flexibility, structural stability, and smooth motion. The arm consists of 6 degrees of freedom, which enables it to replicate the human like action, allowing rotate at the base, shoulder, elbow, and wrist. For the fabrication purpose, we used PLA material and 3D printed all the structural parts. PLA was chosen primarily because of its lightweight, cost effective, easy to print, and mechanically stable for stable prototype level applications. Using PLA significantly reduces manufacturing cost, which makes the device more accessible for rehabilitation centers. To activate the joints, we used MG996R servo motors, which provide high torque output and can handle the mechanical load required for lifting small household objects. These motors were chosen because of their good balance between power, cost, and reliability. Through multiple iterations of the mechanical design, we ensured that the arm achieved smooth motion, minimal flex, and sufficient range of motion to perform pick and place tasks effectively.
So, hello all. So, I'm going to tell about the overall system architecture that consists of a workspace environment with a monocular camera and vision module and an inverse kinematics unit with an ESP32 microcontroller. And the robotic arm consists of a six dock, and the monocular camera continuously captures the workspace the environment in the real time. So the captured video frames are processed using OpenCV, and Euro V8 deep learning model is used to detect and classify the objects based on their shape and size. Once the object is selected and enclosed within the bounding boxes, and the centroid is calculated using the OpenCV. These centroid values represent the object positions in the workspace. So the obtained 2D coordinates are converted into robotic workspace coordinates and fed into inverse kinematics module using TH principle. That means Dynamit-Patenberg principle. The required servo angles of each six revolute joints are computed. These calculated servo angles are transmitted to the ESP32 through pi-serial communication. So it communicates with the pi-serial communication port, and the ESP32 controls servo motors and actuates the robotic arm smoothly and with accurate movements. So the object detection, the Euro V8 model trained approximately with 50 real-time images and 5,000 image datasets, direct objects and continuously tagged with their coordinates are updated in the real-time maintenance precise motion control. To enhance user accessibility, a voice-based interaction system is implemented. The user voice commands are converted into text by GTTS, where Google speech to text, and the commands are used match to detect labels in the JSON data. The JSON database will be stored on the ESP32 microcontroller on the PC which is the user are using. So based on recognized command, the robotic arm performs pick and place operations, significantly reducing the physical effort required to this operation. Thus, thus this integration of AI, OpenCV, processing and inverse kinematics enables a real-time user-friendly assistive robotic suitable for stroke rehabilitation application.
So, as a result, the Euro V8 deep learning model was trained on around 5,000 images across 50 object classes. The model achieved an overall accuracy of 89%, showing reliable object detection performance. The average detection time was 0.99 milliseconds, which makes the system suitable for real-time applications. Object coordinates were extracted using OpenCV and successfully converted into joint angles using inverse kinematics. The ESP32 microcontroller provided stable and smooth servo control with low power consumption. Confidence scores for tested objects ranged from 89% to 97%, and precision recall analysis confirmed strong detection reliability. So, in conclusion, a low-cost AI vision-based 6 DOS robotic arm was successfully developed. The system integrates object detection, inverse kinematics, ESP32 control, and voice-based interaction into a single platform. The robotic arm demonstrated effective real-time object grasping and pick-and-place operations, showing strong potential as an assistive and rehabilitation device for stroke patients. So, in future, depth sensors or LiDAR can be integrated to improve spatial awareness, collision avoidance techniques, and reinforcement learning based on adaptive grasping can further enhance accuracy and autonomy. With these improvements, the system can evolve into a more intelligent and clinically applicable rehabilitation solution. Thank you.